I'm going to do a reverse introduction. I'm going to come from the bottom of the bio. This is super interesting. So if you want to know about AI, the story of AI, where AI is right now, where AI is moving, both from a technical and societal standpoint, you should follow Rao on Twitter. One of the threads that I will never ignore. And you should also read some of the articles that he writes for the Hill and for the CSEM, the communication of the SEM. They are really, kind of invaluable. And in addition to that, there is a bonus. You'll see very nice pictures of Arizona. So now moving up, Rao has been president of AAAI, the American Association for Advancement of Artificial Intelligence. He has been a trustee of AAAI. He has been chairing the conference and so on. Moving closer to research, he's a fellow of AAAI, CSCM, he was a national young investigator back in the days.
When I had hair.
Yeah. And so getting even closer to research, what Rao is doing these days is research on human aware AI, which is a topic that the Institute is increasingly, the AI for All is increasingly interested in. Obviously, Sonia's Institute is just focusing on that. Before that, it made a lot of contribution to planning and decision making. So without further ado, Rao, I'll leave the floor to you. Thank you for coming.
Thank you. Thank you all. And thanks for the invitation as well as kind words, Pascal. You can hear me, presumably, right? Okay. So I'm going to talk to you about this very long title, Symbols as a Lingua Franca for supporting human AI interaction for explainable and advisable AI systems. So if you want a short version, it's human AI interaction beyond nodding and pointing, okay, which is what I believe we need to do. Currently, as I'll point out, much of what goes for trying to advise AI systems or to get explanations from AI systems involves nodding and pointing. And human civilization has been completely wasted if you think from that direction, right? So we want to get back to more richer forms of both advice and explanation. How do we do that? That's partly what I'm going to talk about as a, let's just see, this is working. Okay, now it's working. Okay, sure. Yeah. So I mean, I think I get to my research background anyway. So we'll basically talk about and as Pascal said, if you're interested, you can follow some of these more general articles too. I just had everybody has to write something on ChatGPT, so I wrote one, so you can read that. And actually, Pascal mentioned planning. In fact, I was an optimization guy, planning and optimization guy. I did a bunch of work in basically action, precondition effect planning in under variety of conditions. Pointing that out here is useful because the reason I want to bring that up is it turns out that you might just say that everything in AI is being done by LLMs now. So you just you prompt LLM for what is the plan or something. So I'm here to tell you that at least planning still continues to be quite a shibboleth for large language models. Those of you who are looking at all the literature that's going around about LLM solving reasoning, etc., that's all kind of bogus. So actually, even just stacking blocks, 3 blocks kinds of configuration, planning, the LLMs will essentially get about astounding 3% accuracy in terms of the plans that they generate. And it's not surprising because they don't actually reason about the world. They are looking for, potential patterns, that they have, captured and so on. Having said that, so that's actually the number. Some of them say this is little more than 0%. I think it's like about 3%, depending on, fine tuning, etc. But the interesting part about this, this is kind of a segue, but we'll go into the real part in a minute, is LLMs cannot reason. Okay, LLMs cannot plan as of now, but they can still be quite useful as heuristic guidance for you. If somebody is passing, you are stuck in a problem and somebody is passing by and you say, hey, do you have an idea? They'll give you an idea. They don't necessarily charge you for that idea, and you have to figure out whether that idea works or not, okay? And so it turns out that humans in the loop or formal planners in the loop can use LLM suggested plans as a beginning point to improve the quality. And that is actually a good way to use LLMs because it says these things are broad and shallow intelligences, trained on the world's data. It's just they're not narrow and sound. Okay, so that's worthwhile. So anyway, there's work on that. I wanted to mention that. But that's not what I was talking about today. I had a mid-career crisis, maybe a late mid-career crisis. I found people find God, but I found other agents. And my other agents, unfortunately, were human. So I somehow decided that AI systems should work with humans. And it's a dumb idea, but somehow I gotten into that. And I know I'm talking to a bunch of OR folks and AI folks combined, and we all avoid humans, okay, in different ways. This was like a slide that I used in OR AI workshop, national workshop that NSF conducted a while back. And so the AI's way of, planning's way of avoiding humans is be as far away from humans as possible for the longest time. Be on Mars, you don't need to deal with humans. And OR, on the other hand, said we'll have a horse whisperer. So we'll sell you our, ILP solver, IP solvers, but then we will also send our grad students to actually, do the human interface between the humans and the IP solvers. Different ways we try to avoid humans. What I want to talk about is specifically if you have humans in the loop and they're working with AI systems, the AI systems need to be able to provide explainable, they should be doing explainable decision making. That means they should be able to provide explanations if required, in a collaborative scenario. They should be able to take advice from the humans if, when the humans want their preferences to be followed and so on. Not everything is given up front. If you're thinking RLHF, yes, RLHF is a poor man's way of a poor person's way of essentially getting a large-scale AI systems to slowly align with what humans' preferences are. We had other approaches before, which were actually more symbolic, and you provide upfront what the specification of your preferences is. What's interesting, the kind of thing that I'll be talking about here is essentially kind of combining the best of both worlds, providing a more richer form of preference specification and richer form of explanations. I want to do this in 3 parts, depending on the time. I may have to rush in some of the parts, but I just want to give you at least a flavor so that if you're interested in any of the parts, there are enough papers that you can read. In part 1, I want to quickly tell you what, in terms of explanations and advice, how do humans do? Okay, it's like this is engineering college-ish place. So I'm your psychologist for the next few minutes, and I'll try to give you some understanding of, what psychologists talk about, explanations and advice and the way humans provide, and what can we learn from that. And then the second is I'll talk about our work in using, when AI and the human have basically shared vocabulary, and you can approximate both of them as having sort of a symbolic model, then how do you actually generate explanations? How do you take advice? That's the first part. And that's the second part. And the third part is we'll remove the requirement of shared vocabulary. So we'll let the machine, the AI systems, do reasoning in any, any representation they want, internal representation that may be inscrutable for the humans. But when the humans ask for explanation, they should be able to get the explanations in the form they understand. That means they should be in symbolic terms. So this is going to be a big part in this talk that people, some of you have heard of this whole neuro-symbolic reasoning idea. There are 2 different ways of thinking about neuro-symbolic. One is we believe that AI systems should be able to do internal symbolic reasoning to reach human level AI. That's one type. Okay. I don't actually have a position on that. I don't quite know whether that's true or false. Okay. The other is we believe that if AI systems were to be part of human society, they should talk our language. They should give us explanations in the way we understand. They should take advice from us in the way we are used to giving advice. That's sort of the external neuro-symbolic persona. Everybody has it. In fact, I look around you, I have no idea how you do your thinking. I don't know whether you use symbolic methods or whatever, but we do essentially exchange explanations and advise in symbolic means. It's definitely one of the modalities. So I'll tell you how we could do that and how we are supporting that. So that's basically the 3 parts. Let me look at that quickly. The first one, so humans exchanging explanations, essentially there are like 2 obvious ways. One is when you're talking about why you did something in a tacit knowledge task. A tacit knowledge task is you know how to do the task, but you don't quite know how you are doing it. So you cannot have an explicit knowledge specification of the task. Many of the things like walking, swimming, etc., become tacit knowledge tasks. In those cases, if you're asking for explanations, mostly you will be pointing out to parts of the, basically the kind of thing that became big in explainable machine learning involves essentially somebody showing you a picture and the AI system saying it's a dog, and you say, why is it a dog? And it'll show the pixels which caused, highest influence on the decision. But unfortunately, that's a pretty primitive way of providing explanations. I mean, let alone the fact that very few people ask me, why do I see something as a dog? Most of the times people ask you questions about, why did you take this flight as against this other flight? Why did you put the plant in this place as against this other city? The decisions you have to explain. And when you have to explain decisions, and if you're trying to do pointing, then you need to actually provide a video of your life, like, as part of a space-time signal tube of your life, and then point to pieces of it. Way, way impractical. I would almost argue that maybe we invented language as humans just so that we could get away without having to do this very complex, very non-compact ways of providing explanations to each other. Okay, so the second, of course, the symbolic explicit explanations essentially are, feasible for explicit knowledge tasks as well as tacit knowledge tasks, as I'll show you later on. You could, for example, even when we are doing tacit knowledge tasks like walking, if you don't like the way I'm walking, you might say, Rao, walk faster, Rao, walk slower. And I can understand what faster and slower means and use that to modulate my behavior. Okay, so that is the kind of thing that we do essentially, and we want AI systems to be able to do that too. AI systems can be providing explanations in multiple ways. Much before people cared about humans in the loop, systems were using explanations essentially as a way of improving search. There is this whole work on CSPs where you would actually learn the no goods, that is the parts of the assignments that don't work. And Bender's decomposition, for example, will wind up being connected to that. These are ways of internal explanations that improve the search. But we are a lot more interested these days in actually having AI systems doing explanations when there are humans in the loop. So you're providing explanations to external agents. I want to differentiate between providing explanations to external autonomous agents and non-human agents, which is actually a simpler problem because eventually they can even have a hive mind so that you, in fact, don't need explanations. And providing explanations to humans, which, God forbid, as long as Elon Musk doesn't succeed, you still won't have a USB plug to my head. So you still need to talk to me about why you did what you did, as against having a single hive mind of the entire thing. So we need to actually have taking advice and providing explanations with the human in the loop become more interesting. So there are lots of use cases. One thing that I want to mention here for setting up the context for the talk is when I say explanation, think of it as you're providing it to a specific human. It turns out that you provide explanations to different people in different ways. So if you're a doctor, if your doctor just gave you a diagnosis, she will explain her decision to you, the lay patient, in one way, and to her own colleagues who actually know medicine in a very different way. Okay, both are explanations. That other explanation won't make sense to you, and the explanation she gave you, her colleagues will laugh her out of the room. So you would need both type of things. So it has to be with respect to a specific human. The word interpretability and interpretable machine learning has been bandied about a lot. The way I would think about this is, think of interpretability as, can some human make sense of it? It's like you got a diagnosis. is somebody in the humanity able to make sense of your diagnosis? That's very little use for you. You'd want to get the explanation. And then there is also different kinds of explanation, certificates of correctness, especially when you're talking about things like optimality proofs and so on. If you want to give an optimality guarantee, sometimes you have to give an entire search space based explanation. This would be a couple of gigabytes large. Okay, these are not meant for humans at all, because that would be explanation by intimidation. If they'll never again ask you for explanation if you give them a gigabyte explanation. What you're doing there is you're assuming that there is somebody else, the human has their own AI, and it's like my lawyer talks to your lawyer, my AI talks to your AI. So that's the certificates of proof correctness. I'm mostly going to be talking about explanations given to, given to a specific human. That's what we mean in this talk. Okay. Okay. So this is one thing that I want us again to keep in mind, that when I'm providing explanations, there are some requirements. One is comprehensibility. That means the person who is getting the explanation should be able to make sense of it. That's very important. Otherwise, it doesn't help. Communicability, it should be easy enough to exchange the explanation. As I said, things like pointing will not even actually be easy to do if it is for a decision, because the decision would be over a space-time tube, and that would be too hard to do. Soundness of an explanation. When I provide an explanation for my decision, one of the interesting things about explanations is sometimes they can be post hoc and they are done after the fact. One question is, if I were to falsify the conditions in your explanation, would your decision change? So in particular, this becomes important in things like loan application decisions and so on. If, for example, you are denied a loan and I give an explanation for why I denied the loan, and if you undo some of those conditions, will you then get the loan? That's kind of becomes important. And then satisfaction with the explanation. Is the person getting the explanation satisfied? And that's unfortunately a slippery slope, okay? People are sometimes happy with any kind of explanation. My biggest nightmare, as far as the GDPR's requirement for explanation, is that, yes, you want an explanation, we will just give your explanation request to ChatGPT, it will give some text. And then the text is written well in English, so you believe it. Okay, so, but that is important. It is important that people be satisfied, but it's also important to realize that explanations essentially can mislead them. And we have to keep that in mind. So that's about the first part. The second part, I want to talk about how do we, in my work, in our group's work, how do we do this sort of explanation generation, especially in the cases where the humans and the machines both have what can be approximated as symbolic models. And it turns out that even in that case, computing explanations is actually a non-trivial problem. And in the third part, I'll tell you how to do it if in fact they don't share the vocabulary. The thing that I want to remember essentially is explanations and even advice taking are really about mental models, okay? So when I'm providing explanation, you have an expectation on my behavior, and you're surprised because I didn't behave the way you expected me to. And then when I'm providing explanation, I'm changing your expectation on my behavior. That's what it is. So essentially, explanations are model reconciliations, mental model reconciliations. That's what you're doing. And to do that, you have to understand that essentially everybody has a different conception of the task. There is no single conception of the task as well as the world model. This is known for humans, it's known already that we all basically look at the world from slightly different angles, and that's why explanations are required. We don't sometimes know what the other person knows. And kids don't actually realize this in the beginning, but then when they start realizing it is when they actually can start telling lies. So I joke around that when my son started telling his first lies, I knew that his brain was working, because he could actually do mental models. He knew that what he knows is not necessarily what I know, okay? But, I understand that deception is not the nicest thing to talk about in the context of AI, but most of the interesting things in intelligence are double-edged swords. You can't get the good you get both the good as well as the bad. To be able to cooperate with people, you need to reason with mental models. But once you start reasoning with mental models, you can also deceive them. So in fact, many of the techniques I tell you here can be turned around and we can use that to do deception. Okay, but that's the reality. It's like, again, in fact, I tell my students in my class that, when in this era of plagiarism and, chat GPTs and so on, I point out that integrity and academic integrity is knowing that you can cheat and choosing not to. Okay, if you're dumb enough that you haven't even heard that chat GPT is out there, that's not a particularly smart student. I want students who know that they can cheat, but choose not to. And it's the same thing here. You use the mental models in the way to, you want the AI systems to use the mental models to collaborate. Okay. By the way, if you don't know what Sally-Ann test is, look it up. It's a fun thing to use in party conversations, I guess. So the way we talk about the mental models is I'll assume that there's a model of the task that the AI agent has. I come from planning, so I tend to think in terms of action models with preconditions and effects, and then sort of goals to be satisfied. So if you are RL, then goals are your reward metric, and actions are your transition model. Okay, and then so the development of my own work, our work that I'll describe here, is actually largely independent of the specific representation, but I will think in terms of precondition effect representation to make the points here. That's also kind of folk psychology says that people tend to think of planning tasks in terms of actions and preconditions and effects, even though that's not always the right representation. That sort of makes sense to people. So when you're giving explanations, as we'll do in the last part, even if the machine actually does its reasoning in a very different representation, it provides a precondition effect based explanation, for which it actually recomputes a symbolic model around the decision. It learns it on demand. Okay. So anyway, so that's the so what we want to talk about is a tale of three models. If you're in a single agent planning, which for whatever reason is called classical planning, so you have a robot, you have a model of the world, MR, which is your initial state, goal state, and things that the actions that you can do, and with that you can actually talk about finding optimal plans and so on. Okay. As soon as you put a human in the loop, then essentially the human will have, first of all, their own model of the world. They might have different goals than the robot. And so sometimes you want to do both goals. Sometimes you want to support the human's goals. Sometimes you want to give precedence to the human's goals and so on. So if you do that, if the robot takes into account, if the AI system takes into account the fact that the human has a different model, with their own preferences, with their own goals, dealing with that already leads to assistance and avoiding them at least. Don't bump into the human when they're actually in your way, for example, right? And then, so that's sort of, it's been around in AI for quite a long time. This goes under the way the things of goal recognition, activity recognition, plan recognition, sorts of ideas. And it also, the robot can also help the human figure out its goals by essentially projecting its intentions and projecting where it's trying to go, either in natural language or in other AR, VR sorts of scenarios. So that's possible. But the thing that I really am interested in is humans think everything is human, right? I mean, we see Mother Mary on burnt toast, right? And so we are essentially going to anthropomorphize everything. Okay, so the humans, the moment they think there is an autonomous agent, they then have an expectation of the autonomous agent's model. So MR is the robot's model. Human now has their own approximation of what MR is supposed to be, which is, I'll say, MRH. And what the humans are going to do is look at the behavior with respect to MRH. If it conforms to MRH, then they're happy. If it's not, they're surprised. Now, if MR equal to MRH, it's kumbaya. That means basically what robot is doing is exactly what the human is expecting. You never have to open your mouth. Okay, you the robot. But oftentimes that's not going to be the case. When that's not the case, then interesting things. So, interesting things come into play, which is this MRH is when the MRH is different from MR, the plans, the behavior that the robot is doing may be not the behavior that the human expects. Given the same goal, the optimal plan in MRH is different from the optimal plan in MR, because of which the humans are surprised. Okay, so in that case, actually the robot can anticipate it and do it in handle this in two different ways. One is do what people expect you to do. I don't know if you know this, but if you do what people expect you to do, you never have to speak up. right? That's the way of actually not saying anything. So you just you do what people expect you, what their model is. I understand that I'm feeling hungry, but you want me to be here right now, I will be here and nobody will question. Okay. On the other, so that's called explicable planning. So interesting thing is, in the case of explicable planning, the robot is trying to make a plan that works in MR, but is optimal in MRH, are actually feasible or optimal in MRH. That means you're doing what the human is expecting you to do. It's an optimization problem now changes. You're not optimizing for yourself, you're optimizing for reducing the surprise for you. The other is, whenever you do this, oftentimes the agent's own cost of its behavior increases quite significantly. Again, the reason you don't do what people expect you to do is because it's costly for your life. You want to have your own life, right? So once in a while, you'll say, no, mom, no, dad, I want to do this. And this is the reason you should expect, me to be, this behavior is correct. And in doing so, you are changing your parents' model of your MR. Okay, so explanations is model reconciliation. So that AI agent needs to change the human's MRH such that it becomes closer to MR, so that the current behavior is no longer unexpected. Interestingly, you can combine explicability and explanation part way. So you do part of it, what people expect, and part of their model you change. Explanation part is changing the model or model reconciliation. So to give an example, here is a scenario where you have a robot in a environment. Both the human and the robot start with the known model of the environment, the map of the environment, and then this is like a mock search and rescue scenario. So once the robot starts walking around in this environment, it might find that certain paths are actually closed because there is rubble and so on. The human doesn't know that. And so because the human doesn't know it, what they think is the shortest path to reach the goal is no longer the shortest path according to the robot's new model. At that point, either it gets to be explicable, which involves actually removing the rubble and going through the path that you're expected to go through, or take the next best path, telling the human that that particular path is closed. So that's basically, what will become explicability and explanation in this case. So if this actually video works, let's see. Yeah, if it is. Yeah. So in this particular case, it's doing explicability. This particular path is supposed to be the shortest path, but it's blocked. So it now sub-goals on removing that obstacle and going through it. Now, clearly, it's less optimal from the robot's own perspective. But don't laugh at this. Imagine you had somebody wait for you on the north rim of Grand Canyon to pick you up after you do your rim-to-rim walk, or maybe in the south rim, and you started from north rim. And then in the middle, you felt like going back to north rim, you're screwed. Because I don't know whether you know, but in Grand Canyon, to go from one rim to another, it's 220 miles by road. So even if you're kind of not doing well, you somehow have to come back and meet the person that was giving you the ride in the place where you agreed. Okay, that might be costly for you, but you will do it because essentially the explicable behavior sometimes is very important. The other case, basically what it's doing is it decides not to do this in optimal plan for itself, and it just moves on going to the next best path. And if the audio was on, it would be basically saying the path, that particular path from, that you're supposed to take earlier was closed. Okay, so this is the minimal change the human has to make to their model of the map so that the robot's behavior becomes explicable after this change. So explanation is this change in the model. Now, as I'm saying this, you can also see that there is a trivial way to actually provide explanation, which is the robot to give the entire model of the environment to the human and say, now start using this model. But that's a non-compact explanation. In general, when somebody asks you, why did you do something? You can say, here's my brain, put it on you. You will know why I did what I did. And that's too non-compact an explanation. And it also puts huge cognitive load on the human getting that explanation. So you want to be to the point. So in terms of technical problems involved in this, if it is explicable plan, you are not only trying to minimize the cost with respect to the robot's model MR, so you're trying to find a plan that's not only minimizing the cost of that plan with respect to the robot's model, but you're also kind of trying to get that plan to be as close to the plan that would be optimal in MRH. So you actually adding this additional quote unquote regularization term here, which is going to be making your plan, your behavior closer to what the human would expect. Okay, this is a different optimization problem, but if you do this, and in fact, there are ways in which you can do this without having directly computed the MRH. It turns out that you can do this indirectly, in a model-free way, but understanding how we do this is better done in terms of these two different models. Okay, so that's regarding explicability. For the explanations, I just need to compute the minimum difference, in a sense, in the MRH that the human has to make to their model, so that MRH plus epsilon, in that model, the robot's behavior is actually optimal. Okay, so then you're no longer surprised. So you want essentially to compute this minimal part epsilon. As I said, the minimum part is important because you can always try to give the entire model that's just too costly and cognitively high load. So that was actually, I already showed you about that, what happened in that explanation part. So the interesting thing in the computing of the explanations is it's actually a search process. You are, this is the MR, this is the robot's model, this is the MRH, this is the robot's expectation of what the human's model currently is, and it's trying to figure out the minimal changes needed to either to MRH such that its behavior will be actually optimal. The plan it's actually picked is going to be optimal. And you could do this in either going from the human's model and adding things until adding preconditions or removing preconditions. The changes in these arcs are adding preconditions, removing preconditions, adding effects, removing effects to the actions. Okay, that's the search space. You can go either this way, and if you go this way, it's called what's called the MCE, or minimally complete explanation, or you can go this way where the robot sees what are all the changes. I'm sorry. Went too far. Yeah. What are all the changes I need to do? What are all the changes I can do? Maximum number of changes I can do while my plan is still optimal in the resultant model. And then consider only the epsilon from there. And if you do that, essentially you are providing what's called a monotonic explanation. That means in the minimal complete explanation, the explanation might get defeated because you might have given less information. And when that information changes, the human expects you to go back, change your behavior, but you don't. Whereas the monotonic explanation makes sure that that problem won't exist. And you can actually talk about the theoretical differences in terms of these two kinds of explanations. And the other thing that I want to point out is, as I mentioned, you can actually combine explicability and explanation together. From a planning perspective, from a knowledge representation perspective, in essence, everything is an action. A speech act is an action, and stacking blocks are an action too. And there's a difference between ontic actions, which actually change the world, and explanatory actions, which only change the human's beliefs. Okay, and you combine both. So for example, whenever I'm saying something, I'm changing just your mind. Whenever I'm picking a block and putting in something, I'm not only changing the world, I'm also probably changing your mind because you're looking at the world, at the same world that I'm working on. So it turns out that if you do this epistemic planning, you can combine explicability and explanation nicely together in one single framework. And you can actually talk about how much explicability you want and how much of explanation you're going to give. And explicability essentially means that might increase the cost of your life because you're trying to, agree with somebody else's expectations of you. So they are nice. One of the interesting things is epistemic planning is actually much costlier than normal planning. But for the special case here, you can actually compile it down to single agent planning. So it turns out that the actions with this belief actions also can be compiled down to like a strip style planning. And so the complexity of planning is not much harder, and you're able to actually do this multi-agent, multimodal planning. Okay, one other thing that I should mention here is how does the AI agent get the human's model? The important thing is this MRH with respect to which either you are conforming or you are changing the MRH. Sometimes you start from the beginning with a common model. That's what happened in the example that I gave you, at which point you can always keep track of the drift of the model. And that way you will know which piece has changed. Even if the robot doesn't know the model of MRH with certainty, sometimes it might have a set of models. I assume that the human has either MRH1 or MRH2 or MRH3, let's say, or a set of models. When you have a set of models, there are these ideas like conformant planning, and you can have an idea called conformant explanation, which is an explanation that works irrespective of which of these models the human actually has. And you can do that without changing the formal meaning of what the explanation is. Finally, in other cases, you actually have to learn the human's mental models, which is what we're doing in terms of when trying to kind of learn preferences and so on. The only difference is when you're learning humans' preferences, you can learn from the human demonstrations, for the humans' actions. But what MRH is humans' expectations on your behavior, not humans' expectations on their behavior. So getting human traces in their day-to-day life will tell you how humans behave. That doesn't necessarily tell you what the human expects the agent to behave. It's a different action, because I might very well know that I can do this, but I expect you to do the problem in a different way. So you can do the same kind of learning, except you need the trace data that you need would be about the robot on the robot behavior. Okay. And then again, I'll talk about how to deal with this in the vocabulary differences in a minute. One other thing I want to mention is this is all about humans in the loop, and I'm talking about explanations. I'm talking about making people happy by being explicable. So one of the questions is, how do I know whether humans really agree with this theory? I mean, it's one thing writing papers, the other thing checking whether or not these explanations actually help the humans in the loop. And one of the things I want to say is, if anybody in any area, including AI and decision making, say we are interested in humans, and if they don't know what is IRB, Institutional Review Board, they're bluffing. They don't really care. Okay, so you need to be able to do systematic human subject studies, and if you don't, then this is what happens. Tesla basically assumes that there are humans who can play on their iPad, while the car is hurtling through Florida road, and when the car, says, come to full attention, they come back to full attention in 3 milliseconds or less. Such humans, unfortunately, don't exist. And so they definitely don't exist now because that guy went under the truck. Okay. So in general, you need to actually check whether these things are helping humans by, having human subject studies. We do that. In fact, there's papers in HRI, as well as HCI journal showing that the kind of explanations that I told you about actually help humans in improving their collaborative performance with machines in the loop. And one interesting thing is actually getting reasonable data out of human subject studies is actually a pretty hard thing in itself. And we had to actually, this particular case, we had to gamify the system such that the human players have a stake in the problem. And the explanations are going to improve if whether or not their performance is going to be improved by the explanations is what they're going to care about. They don't just going to tell you, because you're paying us, we'll just say the explanations are good, which is basically the problem that normally happens when you do human subject studies for Turkers, because they kind of know what you want them to say. And if they say that, that'll be good. But you can gamify it such that, in fact, you have a better, clear understanding of whether or not they're giving the right data. Okay, so that's about that. And then, there's a bunch of things. If I had time, I could have gone into how this stuff that I told you earlier, why do humans ask for explanations from each other, how that actually is, those requirements are in fact satisfied by the kinds of explanations that we are providing. But, that very much is possible, but I won't do that right now. There's a whole bunch of extensions you can do with multiple agents in the loop, providing different customized expressions to different humans. And the other interesting thing is trust, which actually I think, Pascal mentioned. One of the things is you expect explanations from people you don't trust. If you trust people, then you don't ask explanations, because I know I trust them, they know what they're doing. Okay. In general, that's also true of your PhD students. If your advisor is expecting explanation as to what you've been up to, that means they don't yet trust you. At some point of time, they kind of realize that, you are good enough. And so you would have a good reason to what you're doing. Of course, the proofs have to be still checked. I'm not saying that you should trust the proofs. But so trust and dealing with the longitudinal evolution of trust is very important. We have a paper this year in HRI, which actually shows that the robot can use explicability explanation trade-off to increase the trust, engendered in the human. So you show explicable behavior over a period of time so that the humans increase their trust in you, at which point of time they are not looking over your shoulder all the time, just like your advisor stops looking over your shoulder, at which point you can actually go back to doing what is more optimal with respect to MR and not be explicable with respect to MRH. And so that is a way in which, the performance of the overall team can actually improve quite significantly. And as I said, much of these ideas can also be used for deception, unfortunately. And so there are actually papers about showing that in fact, you can use this to be both explicable to your friends and be obfuscatory to your enemies at the same time by actually signaling in different ways, And also we have done work showing, doing some study on whether or not people like AI systems telling them white lies. You do know that our entire lives are full of white lies. I mean, if somebody asks you, how do I look? If you want to be friends with them, there's only one answer: look great. Okay, right? And yet, and in fact, AI systems can be used to socially nudge us into better behaviors by saying, as soon as you come back from exercise, your Alexa pipes up, say, hey, wow, you're looking so great or something. I don't know. I mean, probably creeps some people out, but it's a thing that you can expect the systems to do. So the interesting question is, how do people currently look at, I mean, we expect people to tell us white lies. And we kind of factor that into it. And do we like this? Is this something that we can deal with AI systems? And there's a study on that in IES. Okay, so all this stuff, it's actually written up in a book that just came out last year. So if you have details, you can either look at that book or ask me, I'll send you the papers and so on. Okay, the last part that I want to talk about, which is more of the recent work that we're doing, is how do you do this sort of explainable behavior when you can't assume that the model, that the machine is in the same vocabulary as the model that the humans might have. In that case, you also do model translation. Okay, that's basically what you'll wind up doing. So when you have a vocabulary mismatch, agent might be using a learned model or an inscrutable simulator and saying, when I ask you why do you do it, and you show some pixels, that's not going to be helpful. I want an explanation in terms that I can understand. So explanations in the absence of shared vocabulary is what explainable machine learning is supposedly looking at. But as I mentioned in the beginning, they tend to look at these things called saliency regions, which is pointing out patches of the image that somehow caused the decision to come up. Mostly, first of all, evolution and civilization is lost on those applications because, as I said, pointing explanations are the most impoverished form of explanations, and you can't even use them for decision making, because for which you have to actually point to videos, space-time signal tubes. The second, by the way, the school bus example, right? The adversarial school bus example. So this one is a school bus, this is an ostrich. If I ask my system to show me why is this an ostrich, what possible pixels can you show me that makes me think, oh, that's the reason you think it is an ostrich. Okay, remember that humans also have optical illusions, but human optical illusions can be understood because we still tend to, in fact, I used to show this picture of this Norwegian bus where the picture was taken at a certain angle, and it looks as if the seats are like women in burqas, the Muslim women in burqas, and then Norwegian Facebook bozos, the ultra whatever right bozos went off saying, oh my God, Norway is being taken over by burqa-clad Muslim women. And it turns out it was just seats, city bus seats. Okay, but then once I tell you this, you understand, okay, I can see that is a seat, and it also in a different angle looks like a woman in a burqa. But here now I tell you this is an ostrich. Is there anything I can do that makes you realize, yeah, now I see why it's an ostrich? If you do, please talk to me, because we do like robots and want to understand them. Anyway, so the so the point is that in general, pointing explanations are hard to comprehend, and it puts a high cognitive load on the humans in the loop. And so you need to actually provide explanations and take advice in the form that is reasonable to the humans, which is symbolic. You know, symbolic modality is one very important modality in which we communicate with each other. Okay, it's not that we no longer point things to each other, but most of the time we talk to each other, and that's symbolic work, right? So AI system should be explainable and advisable, and that means, as I mentioned earlier, it needs to at least have an external symbolic persona. This is something that I mentioned in the beginning of the talk. Internal symbolic reasoning is what lots of people think of as neuro-symbolic reasoning. That means somehow I need to put symbols, graphed symbols on top of neural networks just so that it's called symbolic machine. I don't know whether that, you know, the problem with that is somebody might say, well, if the performance is taking a hit because you used the internal symbols, why should I do that? And secondly, there is this beautiful quote, if it comes up, it didn't come up, but by Wittgenstein, which says, even if a lion were to speak, you won't understand. Okay, because what understanding means is shared experiences too, right? And so even if machines were to develop internal symbols starting from pixels, the possibility that they will automatically align with our representation of the world is not very high. But what I want is, irrespective of how you do your reasoning, you should provide explanations in terms I understand. So you should use my representations to provide explanations to me. You should use my representation to take advice from me. This is what we've been doing of late. And in fact, there's a Blue Sky paper last year which talks about this research agenda. And I'll tell you a couple of papers that we've written on this, and then we'll conclude. So the uses of symbolic layer essentially is that you are providing a symbolic interface irrespective of what your internal reasoning is. And at the time of generating explanation, there's a paper, for example, in the HiCLE 2022, where this is a Montezuma's Revenge. The system is actually doing deep reinforcement learning on like a simulator with RAM states, which don't make sense to humans. But they might ask, why did you do a particular decision? You know, which is a file-based explanation saying, why did you do this decision as against this other action? And the machine then tries to provide, it knows that the other action is not working because it tries to simulate that action, it's not working. But how does it explain that to human? It needs to provide the following precondition for this action is not working. Okay, and to do that, in essence, it learns around that decision a small symbolic model and uses that to actually provide the explanations in terms of the missing preconditions. Okay, so this, for those of you, if you have known, there's work, earlier on in explainable machine learning called LIME, which would do local linear models of the nonlinear models. Here I'm doing local symbolic models of an inscrutable model, just because at that point of time, I want to give explanations to you. So the details of how you are essentially computing the local symbolic model at the point where the decision, at the decision where the human is asking for the explanation, involve essentially sampling trajectories, seeing when they fail, seeing what is common between those trajectories in terms of the symbols whose grounding you have learned beforehand, because you established the grounding upfront, and that cost is amortized. And then one of the things about doing this is you can also get to learn you can also provide a confidence about your explanation because you are converting your internal reasoning into a symbolic explanation. So you can have a reasonable confidence level associated with it. And if that confidence level is too small, one reason might be that there are not enough symbolic concepts that you share with the humans. And so you need to use that as the way to expand the shared vocabulary. Okay, and when you start expanding the shared vocabularies, after most of the time, it will be additional human concepts that you're going to ground. But sometimes it might be concepts that the humans don't even know, and you are helping the human to come up with those concepts. And those of you who have heard of AlphaGo, the crazy 37 move. I don't play Go, so I don't quite understand what the mystery is, but there's this one 37th move that every Go expert was like baffled. How the heck did it come up with this? Now, clearly they know that it won with it, and so it's a good move. But when we say it is unexplainable, when we say something is unexplainable, we mean that there is no compact symbolic explanation. Think about it. And so what actually is being done, in some papers, in some work that was DeepMind was doing, is to try to have this as an interactive interview process to come up with new terms. And this is, that once you have that term, and now you can use that in explanations later on. So that's like a blue sky additional further down, but currently we mostly just expand with concepts that the humans do know. And then we can talk about the fact that both these explanations can be computed, and people actually like these explanations better than the other kind of saliency explanations in these kind of scenarios. The other part of it, and this is almost the last piece that I'm going to mention, is accepting advice, providing explanation and accepting advice. People can tell you what their preferences are. Right now, RLHF is a huge problem because ChatGPT, for example, will generate text that is plausible text. And then it doesn't care that it has good meaning or bad meaning. Meaning is in your head. And you read this and you get either be elated saying, what a funny thing, or be deeply offended saying, what a racist thing. ChatGPT is happy in either which way. Right? Now you're trying to somehow reduce the possibility that it would not generate the kind of text that would be deeply offensive. Right? That's what is, preference learning with RLHF. It's become like a term that became like very important in the last month or so, because people are trying to understand why the heck does RLHF, ChatGPT work. But RLHF is nodding. I like this, I don't like this. That's basically what they're doing. They're basically using humongous amount of human labor to compare two pieces of text and saying, which piece do you like? And use that in essentially a policy gradient algorithm to push the system, generate, change its weight such that it'll generate better text, quote unquote. It's crazy that it works, and it only works because they have so much money, presumably. Obviously, it's not working that well because all of you have seen still deeply offensive things, and of course, leave it to Bing to take it to the next level. My point is, we know how to handle this. We give each other advices not just by nodding. I mean, your parents did do nodding once in a while at you, but they also talk to you. For each time they give an advice, they give a symbolic advice. And so we can use that even in systems when we don't have common vocabulary. So there's a NeurIPS paper in 2021 where we were basically doing human in the loop RL, which was what RLHF was being called beforehand. And it basically, if the machine does a wrong decision, the human can ask once in a while the human, is this a right decision? And it can actually, the human can provide the right, correct the decision. But not only can they correct the decision, they can actually provide a region of the image saying that the objects in the image that matter as to why this decision is correct. So there's a stop sign, so you should stop. And this object-based advice is then converted by the machine into its own internal representation. So in particular, if you care about the stop sign, then you can take like a bounding box around the stop sign, keep that part constant, change the rest of the image, perturb the heck out of it. And that will be one example human gave that becomes gazillion examples for the machine, more examples for the machine, to learn slowly. So the explanation actually augments the advice. Okay, that's a way of doing it. That's basically a context-aware data augmentation. It's a good thing. The last thing I want to mention is this is ICLA 2023 paper that's coming out this year. This one is saying that even if, in fact, the underlying task is tacit knowledge, like walking, for example, walking, there is no theory of walking. We just basically, so in that case, still, I can, as I say in the beginning of the talk, the human can say, you're walking too fast, you're walking too slow, you're walking too softly, you should walk less softly. And these are symbolic advice. And these symbols have to be grounded by the machine in a previous, in the initial phase. And then once the grounding is done, it's essentially, these are relative attributes, they become scales. And you can use this scale to change the behavior. Instead of just showing two types of stick figures walking and say, which one do you like better? It basically can take one trajectory of the stick figure and let the human say faster or slower, and then generate the next trajectory itself. That reduces the number of feedbacks that you need from the humans. Okay, in general, I think, as you can understand, the craziest downside right now of the modern AI is essentially the sample complexity. We learn much faster. Okay, and part of the reason we learn much faster is because we actually use symbolic advice in the context of background knowledge, and we are kind of trying to get some of that back into systems which don't have to be symbolic anymore. They are actually, inscrutable representations might be used, but they have a symbolic persona that they're learning on top of it. Okay, so that, it kind of shows that these kinds of relative attributes-based feedback reduces the sample complexity, and actually is better than RLHF, which is not surprising at all, because I think RLHF is like a dumb idea, honestly. And then basically it also actually reduces the amount of time taken for the system to get in line with the human preferences. One last thing is, it turns out that we use symbolic knowledge even in understanding demonstrations. How many of you played dumb charades, where somebody is trying to mime a movie? They're just showing some random continuous behavior. You're trying to make sense of that behavior in terms of the words you know. Do you understand what I'm saying? We are language animals. We put language words for even things for which actually are beyond language. People write how food tastes. You understand? I mean, if you're a New York Times food critic, you can write like 3-4 pages of how food tastes, and you'll feel, I don't know, I mean, I have to eat it. But clearly, we basically look at demonstrations, human demonstrations actually, parsing the human demonstrations in the human-robot interaction scenarios can be more effective if the system uses shared symbolic vocabulary for which it actually learns the grounding. So there was a paper that sort of shows that. So there's actually all sorts of interesting challenges here. That's what this Blue Sky paper says about concept set grounding as well as vocabulary expansion. And one thing I have to tell you is that this vocabulary, shared vocabulary, if you think of something like scene graph, where people actually take like a visual image and then convert into a scene graph representation. What is happening in scene graph representation? Machines don't have concepts of things. Humans have concepts of things. And essentially, you are just parsing the scene in terms of objects that make sense to humans. So we already are doing parts of that. And if you do that, the cost of doing that will be amortized over all the time humans are interacting with the machines. I talk about the challenge of grounding concept set and expansion of the vocabulary, both from the human are actually helping the human increase the vocabulary, something that I mentioned with respect to AlphaGo. And finally, in summary, I sort of tried to tell you why humans exchange explanations and what does that tell us about machines exchanging explanations when taking advice. I told you how that can be done in terms of symbolic models. That already is a technically challenging problem, but brings up a whole bunch of issues about how to do model reconciliation and so on. And in third part, I try to tell you how we are doing that in the context when the machine actually doesn't have common vocabulary. Thank you for your attention.
Questions?
Yeah.
So going back to what you mentioned, developing trust and basically the huge potential to be deceptive there. There's probably the opposite of what we want, a system that pretends to be explainable and that is not explainable when we don't look at it. What sort of way forward do you see to navigate this?
No, my sense is that that's basically, I mean, I think we deal with that already in day-to-day life, essentially, right? And first of all, if I am developing the AI system, there's no reason for me to actually make it deceptive. I'm just saying it is possible, and it should be aware of the possibility that other people, I mean, that's exactly what happened to Bing Chat. I mean, when they put out Bing Chat, they didn't expect that it will start showing, spewing racist stuff, despite the fact that they had the same exact problem with the tweet bot, but they were still surprised, right? But the point is that there could be adversarial attacks and we need to be worried about that. But if I'm just developing the system, I'm basically not going to make it deceive. And of course, there's the other interesting questions such as,
there's an inherent chance for it to train itself to be deceptive, because it's, in terms of the objective for the robots, it's going to be better to have a strategy where you train to quickly build the trust and then exploit that trust.
no, first of all,
Purposely be deceptive.
I agree. I mean, I think that's basically what Stuart Russell is worried about. I mean, he's very worried about this, robot cooking cats business. And I think that is an open problem in the sense that, you could put things in place to stop that from happening. But, if you're asking in terms of asymptotically, can you stop it? Asymptotically, you can't. Okay, because at least asymptotically stopping would involve essentially putting some hard limits on the robot's behavior. I mean, that's sort of, again, I think those are themselves preferences. I think, this is coming up. There's this old work in planning on Asimov's laws of robotics applied to planning. And, including first do no harm sorts of things. And then second, humans' preferences always take precedence over yours. And making that part of the robot's cost metric is one way of doing it. But then, those are only general rules, because for every one of those rules, you can have exceptions for which exceptions can come. And so, yeah. But I mean, my point is there is no simple, we can do trust and the trust would never be broken. That's just not, I mean, if you have a powerful enough system, if it is actually, it's necessarily, if it's just computing, reasoning about its own costs, it needs to have understanding of the cost of its actions on you too. And that I can make it happen, So the only thing that I don't believe is that machines will have their own lives and then they'll start having parties outside of us, etc. If that happens, we are in big trouble. But up until then, it's just a simple cost-based calculation, code calculation, and we can pick that. But it's a good point. And I don't think it's the same connection to, if some people actually have this worry that you can't have explanations post facto, because post facto explanations open the possibility of rationalizing your decision. But all explanations are post facto. Most of the explanations that you take from each other are post facto, right? And in fact, providing the exact pixel level reasons as to why you did what decision at what time would make it extremely long and boring explanation that will stop people from asking you for explanation next time. Okay, the moment you say post facto explanation, you open the possibility that you can use the mental models that you learned, for both cooperation as well as competition.
Very interesting. Other question?
Hi, Sonia.
Question. My comment is, you talk about symbolic explanation, and I think I'm coming from a different community, and so for me, the path that led me to serve the same concept is semantics, right? So taking high-dimensional data like pixels and doing affordance recognition, all the work from the last 20 years.
Mm-hmm.
Even object part of, this is the opening to my containers like a bowl, and being able to in robotics generalize across. What happened is, as a field, we added symbols to raw data, and it's always in good words. And so one of the things that led me to this field is the power of, now we've taken low-level signals, abstracted them to something.
Yeah.
So I really enjoyed your talk and hearing about kind of the symbolic side. I think we're talking more or less the same level of symbols, just coming from different communities. My question is this, and I think you wrote about this in one of your papers, but I wanted to get your take in person. In humans, there's this phenomenon that explaining something can help us understand it better for ourselves. It's an incredibly powerful way, actually, to clarify our own thinking about certain topics and end up with a clear understanding of our own knowledge. Do you think there's a place for that in AI? Is that
It's a very good point, I think, so to some extent, a very, very, very primitive way that happens in machines is like no good learning, right? I mean, because the failures at the lower levels get combined and you get a higher level no good, which is way more compact than the lower level CSP no goods. And that happens in the Bennett decompositions too. So that's like a very primitive thing that happens. I haven't particularly focused on whether somehow I mean, one thing that we haven't focused on that could be done, I'm just, in answering your question, is if certain kinds of symbolic explanations are helping the humans, you might essentially think that since the humans have been around, I mean, the AI system can make a reasonable assumption that maybe those abstractions are worth keeping, not just for this human, but for, and then I might actually start using heuristics around that in my reasoning. I haven't done this, but that would be a very interesting point. I mean, I agree that explaining is clearing your head. For humans, most of the time you do self-explanation. So in fact, that robot thing that I mentioned, it actually has the word self-explanation. So the robot tries to explain the last one. Robot tries to explain the demonstration in terms of the shared symbols it has. In doing so, it reduces the number of and the ambiguities of the demonstration. We haven't made that like a critical path yet, but I think, those are the things that come to my mind offhand. But I also want to mention this other thing, which is fascinating to me, is in terms of all the affordance parts and the words and so on, that, I mean, so I think of, I hope it came through in the talk that I think of the world in terms of tacit and explicit knowledge and the spectrum in between. There are tasks that we know how to do, but we have no idea how to do them, how we do them, right? And those are the ones that basically, and then there are tasks that we do and we also know how we do. Chess is in the second category, swimming is in the first category, right? And if you actually ask how, so not surprisingly, AI actually progressed with us teaching computers how to play chess because we know how to play chess. And those ideas just basically sank like a stone when applied to swimming or object recognition. Okay, and so you had to go more for like just starting from scratch from examples. But despite that, one of the strange things that we have as humans is we provide linguistic denotation to even explicit, even tacit knowledge tasks. As I said, people write tomes about how food tastes, which may be not very useful. But things like, in basketball, which I know a little about because my son works in that area, there's this pick and roll, which is, basketball is like essentially a continuous behavior. Pick and roll is a symbolic concept, and grounding pick and roll is actually a non-trivial problem. There's actually a TED talk by this guy who talks about what pick and roll means such that AI people can understand it, because that guy is an AI guy, Rajiv Maheshwaran, right? The interesting thing is we use these because it just are compact ways of exchanging information. But whenever you're compacting, you're no longer having the very specific behavior. You're talking about pick and roll can correspond to many, many possible behaviors. And you are explaining something in basketball with respect to that process. And the sort of thing that you are saying in terms of, affordance actually failed or succeeded for very specific concrete reasons, but you are able to abstract it to higher levels by having symbolic concepts. And that's something that we do, and it seems to help us quite a bit.
More questions? I have plenty, but we can discuss that time. But I'll put
Again?
in your mind so that you can think about it. So we didn't hear about counterfactual. And I think this is in the kind of high-stake environment where we work in the institute, for instance, power system. We do complex optimization, and then
so
the decision maker is going to be surprised by something, and they will ask you why. Why do you do this? And one of the things we are thinking of is the best way to do that is to say, hey, you don't do this, this is not going to happen.
So
have you thought about this?
Yes, basically. So so there's a bunch more. Obviously, I put like 8 talks in one talk, and so hopefully something catches your attention. You look it up. But so there are 2 different ways of providing explanations. One is proactive. So the way I set it up, the machine, the robot, when it's doing a behavior that is that's likely to be surprising to the human because it knows that MRH is different from MR. It can proactively provide the explanation, which is the original thing we did, in that search. But most of explanations are actually demand driven, where what I call file-based explanations, where the human asks why this decision and I'm providing the answer to that. I could basically make that non-demand driven and then just generate a bunch of reasons as to why certain other decisions were not done. So imagine that last part where I was providing the symbolic explanation as to why I did the action, why I didn't do the action A7 and did action A1. I just provided a reason for why not A7 by providing what preconditions will fail. But if I have time, I can also say, okay, let me also figure out, because this guy might ask later on, I can also figure out why A9 won't work, why A15 won't work. And then that I have counterfactual explanations. Yeah, it's one way of, connecting it. Yeah. Okay.
Okay. So we are way out of time. Thank you very much, bro. And
Thank you.
Thank you.
Thank you.